Okay.
9.5.
First person we've got to talk, or the first one, or the one we're talking about today, Darwin. Not Darwin. Darwin. He's the first person who gave us evidence for natural selection. He's not the first person who came up with the idea for evolution. He's the one who came up with all the evidence behind it. Did all the groundwork. Because he was going on a trip on his favorite sailing ship. Sailing through the seas. I don't know what to say here. But it doesn't rhyme. Okay. So, his evidence for natural selection. And what natural selection is going to be, it's going to be the most...
You know what those red lines mean, right?
No. Natural selection is going to mean the most advantageous traits are passed from generation to generation. What? In my opinion, it is.
But he has a degree.
You're going to get intimidated by some of these questions, though. Slow down. You have plenty of time to read the questions and think about what it's asking you, because there's only 13 multiple guess questions, but a lot of them are going to have like a full paragraph and then a graph after that. Kind of like the POGIL, and the reason why is because there was a lot of these on the AP exam. I want you to get used to comfortable realizing, okay, just because this is intimidating, just because it has scientific names of these organisms in here, and I don't have any clue what those means, doesn't mean you need to panic. All right? You have more than enough information to go through this that's given in that paragraph and from that data table or that chart or that cladogram, stuff like that, that you can figure out the answer from the common knowledge that we have in this class. It'll be intimidating, but I need you to just slow down and think about it. I promise you, the questions aren't that hard if you slow down and think about it. Abel? Yes. Before the AP exam. So, it's going to go Unit 8, review for the AP exam, final AP exam.
Do you always have a No. So you just decided to be surprised? I'll take my $100. What is our final?
Why is everyone so spicy today?
I'm supposed to be eating food and playing.
On the actual day of the final, it is that.
I had no final, and I had final every class.
Okay. What, Chris? Why are you so... What's wrong? Get your grade high enough that you don't have to take them. All right. Anyways, there must be genetic variation. And then finally... Not traits that are inherited in the organism's lifetime. Let's say Elisa decides after high school, she's going to go get them big body gains. She's going to get into women's bodybuilding. And she gets yoked. All right. So she's super ripped and everything. Those traits wouldn't get passed to her offspring if she has babies because those were acquired in her lifetime. Okay. So traits that are acquired in a lifetime don't get passed on. It's got to be something that's in her genetics. Yep. So, like I said, yeah. If it's something that you did, you work towards something like that, it's not something that's going to get passed on, something that you're born with. And so this genetic variation, do you know what the biggest cause for genetic variation is? Mutations. Mutations drive evolution. Okay? So mutations are going to drive evolution, and we have this, for some reason, there's a negative connotation with the word mutation. It's not a bad thing. Sometimes mutations are advantageous. All right? That's what creates this variation. So we've got to talk about some evidence for evolution. All right? Evident. This is all just part of... I wouldn't put it under Darwin. So, evidence for evolution. The biggest, most common first one we're going to talk about is called homologous structures. That prefix being homo meaning same. All right. So homologous structures is going to be, same structure, different function. Okay, same structure, different function. An example of that being a bat wing or a human arm or a cat's leg or a whale fin. Any clue why these are homologous? Cats have 4 of them. If you look at them structurally, if you look at the composition of a bat wing, it's got a radius, it's got an ulna, it's got carpals, metacarpals, all those structures. It's got the exact same structures in there. They may be shaped a little bit different, but compositionally they're made of the same thing, giving evidence of a common ancestor. All right? Evidence for a common ancestor, and it's called divergent evolution, meaning we had this common ancestor and it split into these different organisms. Where it was located at, the environment said, hey, you live in the ocean, it's going to be really, really, really beneficial for you to have a fin. Turn this into a fin, all right, over millions of years. Or it would be over millions of years they developed a wing, okay? So because of where the environmental pressure for that was located at. Okay, so this is evidence for a common ancestor, and it's called divergent evolution. We also have something called analogous structures. S-T-R-U-C-T-U-R-E-S. Okay, with analogous structures, they are different structure. I can't spell. Different structures, same function. An example: a bat wing, a bird wing, insect wing. Analogous. All right. So analogous structures, they don't have a common ancestor. Meaning there was environmental pressure for them to develop these structures on their own. So these are what's called, the other one is called divergent, meaning we had a common ancestor and they split out. This one means they don't have common ancestors, but they started to evolve similar structures. Meaning this is what's called convergent evolution. Romero, you want to borrow my glasses? Okay. All right. Finally, we got one last one we got to talk about. No, this is just for evidence. Convergent, meaning they come together. They had different ancestors, but the environmental pressures caused them to all evolve the same traits. Okay? Or same structures, I should say. All right. So, fossil evidence, what we've got for this. Sorry, my computadora is dying. I am on the inside. We are all doing that, though. Let's say I've got a lake. Horseshoe Lake. Oh, yeah. I love me Horseshoe Lake. And in this lake, or we're looking at this, let's say, rock type. Let's say I've got this rock barrier right between it all. All right, that's separating these parts of the lake. Okay? And it's a giant turd. So I've got different layers of this thing, of fossils, let's say. Let's say I'm looking through the layers of the rock in there and the fossils and everything. Let's say this is A1, B1, B2, A2, A3, A4, B4, and B3. If I wanted to see the most recent fossils, which layer would I look in? A4 and B4. Okay, I'd look in both of them. Okay. A4 and B4. No, you're right, Rubes, you're right. So I'd look in A4 and B4 because those are the two top layers. They're separated though. This would be like, so there's a physical geographical separation between the two right here. So they're separated from each other, but they're on the most recent part. So it's kind of like the dirty clothes pile in your bedroom. Where's the dirtiest clothes? They're on the top. All right. The most recent clothes are on the top. I'm sorry. Yeah, the dirtiest, oldest, nastiest ones are probably on the very, very, very bottom. All right. But the most recent ones are on top. That's what I meant to ask, where the most recent ones are. My question, let's say we're looking at time. So this is the newest. This is the oldest. Let's say I put an organism right here. And I find this fossil. What layer do you think I would look in where I would find the fossil that resembles it the most? The answer is B2. Why? It's the same time period. Meaning the chances are they've evolved to adapt to that environment around the same time period. So that would be the one that has the most similar fossils for that time period. Very good. Okay? So that's looking at the fossil evidence for evolution. And so now we get into, we're done with fossil evidence. Now we get into relatedness. Relations. Did not have relations. Organism A, organism B, organism C, D, E, F, and G. And we're going to look... What the French nugget? Let's look at that common ancestor, that common ancestor, that common ancestor, and that common ancestor. And let's give them a number. 1, 2, 3, and 4. So if I looked at these common ancestors and I said 1, 2, 3, 4, A, B, C, D, E, F, and G are all current organisms, let's say. Okay? If I'm looking at this for current organisms, for common ancestor number 1, which 3 organisms share that common ancestor? So which organisms have a common ancestor number 1? A, B, and C. Because they all branch off of that one. So what common ancestor number 2 gave rise to which 3? D, E, and F. Which organisms would have common ancestor number 3? D, E, F, and G. All right. And then finally, number 4. Which organisms would have common ancestor number 4? The ones that are graduating high school because they're A through G. Okay. So all of those have that common ancestor. And so if I were to look on here and I were to ask you, let's look at organism F. Is organism F more closely related to E or to G? Organism F is more closely related to E. They share a common ancestor that's more recent. All right. Is organism F more closely related to G or to C? To G, because they share a more recent common ancestor. Okay? So that's how you can kind of look at this and kind of read this thing right here. All right? Any questions on this one? All right. So we're going to do a cladogram real quick to solve one of these simple ones since we haven't done one for a while. It's a basic one. If you were to have one of these on a test or on a free response or anything like that, Like on the AP exam, there was one of these in 2014. I think it was 2014. But either way, they give you the skeleton for it. So to make your cladogram, they give you the chart, and they give you the skeleton to make it. So that way, you don't have to draw it on your own. So let's say I have this right here, okay? And I'm going to make a cladogram from it. So, like if you got this on a test, it would look like this. You have that, 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 that. Okay? So the first thing we've got to look at is what trait is the most common one. What trait encompasses all the organisms on this chart? Okay, if I look at this, it's going to be vertebrae. So right here would be vertebrae. Is there an organism that has only vertebrae but doesn't have any of the other traits? Shark. What do you say shark in Spanish? What? Oh yeah, I knew that because the Hyundai Tiburon. All right, good to know. So we're done with vertebrae and we're done with shark. What's the next one that encompasses the most number of things? 2 pairs of limbs. Is there something that has 2 pair of limbs and vertebrae but doesn't have any of the other traits? Bullfrog. It is a Bret Hart bullfrog. Okay. And then, as you can tell, we got a mammary, which goes to kangaroo. And then we go to placenta, which then goes to human. Okay? Any questions on how we got any of those? It's possible. You need to know how to. Okay. Let's say I've got 3 organisms now. We're going to talk about allele frequencies and stuff like this. Let's say I've got an organism called a pica. It's a real organism. It's the organism that Pikachu is derived from. And let's say picas love altitudes above 8,000 feet. So they love altitudes above 8,000 feet. Let's say I've got a rat. I don't want to draw it in that color. Okay, let's say I've got a rat. And they love altitudes below 2,000 feet. And then let's say I've got a squirrel. And they love, if it's above 6,000, they die. If it's below 2,000, they die. So they like this middle ground. They love 2,000 to 6,000. Okay? That's not true about the squirrel. The only one that this is actually true about is the pica. They don't like below 8,000 feet. They can actually die if they go below 8,000 feet within a certain number of times within a certain time frame. Because of the temperature, they can die. They're pretty sensitive. So the pica population is actually rapidly declining because of global warming. Let's say I put this on a graph, though. And let's say right here, I've got I've got number of organisms, and right here I've got altitude. I've got 0 feet, and I'll put it in feet. And I've got, let's say, 10,000 feet. Okay. What do you think the population at 0 feet altitude, what would the population of a rat be? Howdy. Why, thank you. Okay. So, do you think that is your girlfriend? Okay. Would the population be high or low at 0 feet altitude for a rat? It'd be very high. And what do you think would happen as the altitude goes up and up and up? It's going to go like this. Okay? What do you think it'd look like for the pica? It's going to say 0 across the whole thing?
No, 0
At 0 feet altitude, it's going to be there, but what's going to happen as I go up? Oh. It's going to go up. What do you think it would look like for the squirrel? It'd go what? The squirrel would go... The squirrel would go like that. Because it's showing that it really likes that middle altitude, but anything too high and anything too low, it dies. Okay? So, that's very good that you can start to realize that. So we'd start having different frequencies of alleles for these different genes and different things. So if we start looking at allele frequencies now, we've got to go into that. And you're going to love this part. Yep. Hardy-Weinberg, meaning P plus Q equals 1 and P squared plus 2PQ plus Q squared equals 1. Anyone remember what P stands for? P is going to be the population, or the frequency of the dominant allele. Meaning Q is going to be the frequency of recessive allele. P squared is going to be the percent population that is homozygous dominant. 2PQ is going to be heterozygous. And then Q squared is going to be percent pop homorecessive. Okay. I'll let you finish this, and we're going to do a practice problema. So let's say color blindness equals recessive. And let's say 81% of the population is colorblind. What percent is heterozygous? For colorblindness. That's our question. So remember, when I'm doing this, I go P, Q, P squared, 2PQ, Q squared. Okay, so that's what I do. I've got to figure out first, what did it give me in this thing? Told me 81% of the population is colorblind. Colorblindness is recessive, meaning it gave me Q squared. So I know that Q squared is going to be 0.81. If I know Q squared is 0.81, if I find the square root of that, I can find Q. So I know Q is going to be 0.9, meaning P is going to be 0.1. P squared is going to be 0.01, and 0.9 times 0.1 is 0.09 times 2 is going to be 0.18. So the question is, what percent is homozygous for color, or heterozygous for color blindness? What's our answer? That right there, meaning our answer, 18%. Let that sink in for a minute before we do types of selection. Any questions on Hardy Weinberg? All right. How many what? I don't know. I haven't written it yet. Probably 4 or 5. Types of selection. So we can have directional, meaning, let's say I've got this right here. Here's my original bell curve. This was like one of the questions on your Pagil yesterday, having to do with the moths and if the environment changed colors. Let's say this is really light. Let's say this is really dark. If the environment were to get darker, what would happen to this entire bell curve? The whole thing would shift to the right. All right, meaning the whole thing shifts one direction. That's directional selection. Then we can also have disruptive. What? You don't get it? So let's say I've got this population of moths. All of them are tan. We build a coal factory in the area. It starts spewing out all this soot and everything, and all the trees get darker. If those moths don't get darker, they die. So overall, the entire population of moths is going to start to get darker, so that whole bell curve is going to shift to the right towards one thing. Does that make sense? Are you just saying that to humor me?
No.
Okay. Then I can have disruptive. The best thing for disruptive, let's say here's my original population, the rock pocket mouse. Do you remember how many types of rock pocket mice did we have? Not one, but 2. We had dark ones and we had light ones. All right. There was no middle ground there. We had dark ones and we had light ones. So if it lived in the shade, it liked the dark one. If it lived in the sun, it liked the light one. So it would actually change from the original bell curve to this. That's disruptive selection. That middle ground is not chosen for, but it actually likes the 2 extremes. And then finally, stabilizing. With stabilizing, it's kind of like human birth weight. Let's say I've got this right here. What actually happens with stabilizing selection, it favors the one that's in the middle. So with human birth weight, it favors 6 to 8 pounds. If it's too light, the baby oftentimes doesn't live. If it's too heavy, the baby oftentimes doesn't live. Okay, so it can cause complications. So it favors that middle level one. Okay, that's stabilizing selection. So all of this is stuff that can happen with natural selection, but there's another one we didn't talk about called, I'll just go with it. I have no clue on that. Okay. With all these other things, it's nature choosing. Environment changes, you respond to the environment, otherwise you die. All right, or your species gets wiped out. Artificial selection is different, though. All right, so for natural selection, it's like, hey, the environment's getting darker. The ones that are darker are going to live longer and have more babies and pass on those dark genes. That's great. Artificial selection is like, hey, I really want this, so I'm going to choose you and I'm going to choose you. Now kiss. Okay? And we choose who does the mating. That's artificial selection. That's what we do with dogs. It's like, I got this dog that's really furry, and I've got this dog that's got this flat face, and I want a really flat-faced furry dog, so now kiss. That's what we do. So we choose who mates. We do it with plants, we do it with animals, we do it all the time. That's artificial selection. We even do it with people. I want a little mocha baby, so I'm going to choose this. That's why I thought of it, because I was looking directly at you when I thought of that. Okay, so we choose who mates on there. Okay, and then finally, we've got one last topic we've got to touch on before we're donezo kabunzo, called speciation. Speciation is when we give rise to one or more new species. All right, and there are some things that can cause this, called like prezygotic. All right, our barriers that we had, prezygotic. So we can have allopatric and sympatric speciation, but some of these are prezygotic. All right, so this was what that little foldable you guys made was on these barriers. So we can have geographic isolation. Meaning they physically can't get to each other. We can have habitat isolation. Meaning, yes, we live in the same area, but we don't ever cross paths. Where geographical, they physically can't get to each other. We can have temporal. Meaning, they don't mate at the same time of the year. They're not reproductively active at the same time of the year. We can have behavioral. Meaning you may not do the right dance, you may not do the right song, you may not look look good enough. We can have mechanical. Trying to put a square peg into a round hole. Sometimes the parts just don't work right. And we can have gametic. The gametes can't bind. We can't form a zygote because the gametes don't work right. And then finally we've got post-zygotic, meaning yes, fertilization did take place, but we can have reduced hybrid viability. We can have reduced hybrid fertility. And we can have hybrid breakdown. Good. And all of these can lead to speciation, meaning it gives rise to these new species because there's something causing them to not mate anymore. It could be there's physical separation between them, or it could be, yes, they are able to mate, but their gametes don't work right together. Okay? Any questions on any of this? Yes. Yes.